Alright, so in this video, I'm just basically gonna show you how you interchange between boundaries of integrals. Okay, so say we have a double integral from x to 2 and then 0 to 2. Let's just keep our integral as simple as this. Say you're integrating a function of x and y, and your integral is given with y first and x first. Let's say this function, to solve this integral, it was easier to integrate with respect to x first. So we technically want to interchange those boundaries of integrals such that we can rewrite that integral as the integral of f at xy dx dy. So how do we find these values here such that this integral will be equivalent to this one, or it will be equals to that one? So okay, let's check what's happening here. Here, notice that your first, this one is associated with this boundary is associated with y. So we're basically saying that y goes from x to 2, and at the same time x itself, this boundary is here, they're associated with x dx. These are the boundaries of x. So we're just basically saying that x goes from 0 to 2. Any relationship between these two, notice that we can basically say our function is just y equals x, and that way if our x is 0, then we go to 0, and then if our x is 2, then you get the upper boundary with 2. So remember, these two must technically agree with each other. So we're going to graph our function y is equals to x for the interval where x goes from 0 to 2. So x goes from 0 to 2, and we're going to graph our function y is equals to x. So this is technically our function like that, and then here you'll have 2 there. So this is the graph y equals x. And from this integral here, it states that y goes from x to 2. This is the line x, and y goes from x to 2. So we're basically looking at this region from our function here. We're basically looking at this region here, and x goes from 0 to 2. So we basically have this region here. And now we want to change those boundaries here such that we can integrate with x first. When we look at this area here, let me just draw the same area again. So we have this. Region here. We want to integrate with x first. So if you look here, x goes from the line 0. This is, remember, on the y-axis you're basically having x equals 0. So x goes from 0 to the line. Notice that x goes from 0 to the line everywhere throughout this. X goes from 0 to the line. So x goes from 0 to the line, y equals x. Solving for x, you just find that x equals y. So we're just saying that x goes from 0 to y. So we can then rewrite that x goes from 0 to y. And then what happens to y then? Y just technically moves from 0 to 2 if you check. So we can rewrite this integral as this integral. So this integral and this one are just basically the same thing. Okay, so let's try another example. Let's escalate things furthermore. Let's say now we want to find we want to switch the boundaries from of this integral, where we have this something like this, f at xy, let's say dx dy, or let's say dy dx, because I already wrote root x here, dy dx, stuff like that. So if we have this integral here and we want to start with integrating with respect to x first, so basically we want to rewrite this integral as the double integral of some function of x and y, dx dy. So we basically want this boundary such that these two integrals will basically be the same thing. So let's look. Y here, dy, remember these boundaries here are associated with y, and the outer one are associated with x. That's basically what I said here. So now if you look here, y goes from root x to 1, and x itself, it goes from 0 to 1. Notice that the function y equals root x matches that, because if x is 0, then we just basically gonna have 0, and then if x is 1, we're basically gonna have okay, let me restate that. If x is 0, we're basically gonna have y being 0 as well. This technically implies that y will move from 0 as well. But notice that the upper boundary, if x is 1, we plug in 1, the square root of 1, it's 1. So this technically works. So we can basically know that our function is just y equals root x. And if we graph the function y equals root x, we have something like this. And we graph it on the interval between 0 and 1. So we go from 0 to 1. And notice, what does this say, basically? And we know the square root of 1, it's 1. What does this technically say? It says y goes from root x to 1. and this is the graph y equals root x. And if you don't want to write y equals root x, you can just say this is the curve x equals y squared. If you square both sides, then you can technically get that x equals y squared. And this one technically says that y goes from root x to 1. So we go from root x, from the curve to 1. We go from the curve to 1. Now, what we want is to rewrite that integral starting with x. If we start with x, notice that x goes from the line 0. Here we know that x is technically equal to 0. So x goes from 0 to the curve. So x goes from 0 to the curve y squared. And when we are done on that, notice that y technically moves from 0 to 1. So that will be when you interchange those boundaries up there. Okay, let's try another example. So if we escalate things further, let's look at this one. So we have 0 to x sine x, and then 0 to 1, and we want to start with x first. So if we look here, it's not really a big deal, really. We want to do a double integral of that, but now we want to start with x first. If you want to start with x first, then let's look at this. Notice that here y goes from 0 to x sine x, and then x goes from 0 to 1. So notice that the graph, if we say y equals x sine x, it tends to agree with that, because if you plug in x is 0 here, we get that y is 0. So this point technically agrees with our function here. So if you graph y equals x sine x, this is technically implying that x equals sine y. Basically just switch the trig function on both sides, then you just get that x equals sine y. So we're gonna graph this, and now I'm just gonna have my x-axis here and y-axis here. Notice that this basically it's not change. You can like play around with what the y-axis on vertically and the x-axis horizontally and stuff like that. It doesn't really matter. Just basically switching the coordinate plane around, so you can still graph y against x. It's a fine thing, but in the end we're supposed to get the same answer, you and I. Okay, so if we have this, then and we graph x equals sine y, and then we technically have something like this. But notice that you don't just start graphing your function like this. Let's look at this one. It says that x goes from 0 to 1. So that's where we'll sketch our function 0 to 1 there. And then y goes from 0 to x sine x. And where's x sine 1? We know that that's pi over 2. So we basically have that. And this function technically says that y goes from 0 to the function. It goes from 0 to the curve. This is where y is 0 in my Cartesian plane, and it goes towards the curve. And similarly, if we look at this one, if we look at this function here, then we technically get that if you want to start with x first, notice that x goes from the curve to 1. X goes from the curve to 1, and that curve is defined by x equals sine y. And technically, we just get that we have that integral going from the curve to 1. So you're just basically going to have sine y towards 1, and when we are done with that, y tends to go from 0 to pi over 2. So we basically have something like this. So yeah, that's technically what we have. So now here's my question to you. I'm just gonna take this. So I'm taking this one here, sine y to 1, 0 to pi over 2, f at x, y, dx, dy, and I tell you, switch the order of integration. Just switch the boundaries of that. Integrate with y first. You already know the answer is that, but I want you to just go and find that. So how do we go about and do that? dy dx. We are going back. Notice that here it says that x goes from sine y to 1. So we have x, and x technically goes from sine y to 1. And then y goes from 0 to pi over 2. So the function x equals sine y tends to ought to do that, because if we plug in, so if x equals sine y, okay, so let's just draw that curve here, x equals sine y. So that's because this curve tends to agree, because if pi over 2, if y is pi over 2, plug pi over 2, you're just technically going to get that x equals 1. So it tends to agree with that. You must check. So if we graph x against, if we graph y against x, then we technically have this. And what this function says is that x, so, and then we can just get pi over 2 there, and then we get 1 there. So then you know what to do from here. Use this to show that you can rewrite this one as this one, of it which you already have the solution to that one. Now my question to you is, if we have this integral like this, 0 to 1, 1 to 3 of f at xy dy dx dy dx. How can we rewrite this integral here, starting with x? Well, notice that these are constants here. So as long as you have constants, you can just basically just switch the values around, no problem. 1301. Only if they're constants. So that's what you have then. And now the coolest thing about a double integral is you can do this. You have the integral of 0 to, let's say, a to b, or let's say b to a. Okay, let's just do this. Let's say you have a double integral from b to a, and from d to c of f at x, y, dy dx. The coolest thing about this is that you can rewrite this as the integral from a to b, c to d, f at x, y, dy dx. Now you tell me, why exactly am I doing this? Notice that if you switch the boundaries on the integral, you have a negative sign, and you also, if you switch the boundaries of the other integral, you also have a negative sign, and negative by negative is technically positive. So this is the other thing that you need to familiarize yourself with. So basically you can be able to like switch the boundaries. Why do you want to switch the boundaries? Because there are some integrals that are hard to integrate, especially starting with some variable instead of another. So if your integral is simple like this, then you can integrate without switching the boundaries. But if it's simple to integrate when you're starting with x first, then you can basically switch the boundaries. And in the next follow-up videos, we're just going to be technically evaluating double integrals, and that's where I'm just going to basically show you like this application of just basically switching around the boundaries. Okay, so yeah, thanks for watching. Don't forget to share and subscribe.